Unsiloed podcast is produced by University FM, elevating the stories of your institution.
Welcome to Unsiloed. This is Greg LeBlanc, and I'm here today with Sam Arbesman, who is scientist in residence at a company called Lux Capital. And also, I like Lux because, here at Berkeley, we have our logo, right? Fiat Lux, right? So anyway, and also a fellow at Case Western University School of Management, the author of a bunch of books. The most recent book is this one called The Magic of Code: How Digital Language Created and Connects Our World and Shapes Our Future. And then previous book was called The Half-Life of Facts: Why Everything We Know Has an Expiration Date. And of course, another book called Overcomplicated. Welcome, Samuel.
Thank you so much. Yeah, great to be chatting with you.
So, this book, Magic of Code, it's kind of trying to, re-enchant us when we encounter software and computation. And, we all know that ever since Max Weber, right, the world has been disenchanted.
Exactly.
And yet, I think for those of us who encounter, say, generative AI for the first time, we think of it as magic, right? There's an element of magic to it. And I guess maybe once we get used to it, we kind of lose that sense of enchantment. And so we need to get something new to kind of get us restarted. And I think you're saying like, hey, let's go back and just look at everything with fresh eyes and realize how incredible and how magical and how special it is, these technologies and tools that we're using. So first of all, I guess the question is, why do some people find it enchanting and others not so much?
Yeah, that's a good question. I think the way I think about this, in some ways, the enchantment part, and maybe it depends on when you first got involved with computers, but I also feel like, at least right now, the conversation around tech is a little bit, maybe, I don't know if it's broken, but certainly it allows us to slide much more easily into the disenchantment and certainly the worry and the concern. When we talk about technology nowadays, there's always this undercurrent of an adversarial position towards it, worry, concern, thinking that it's going to destroy various aspects of our world. And the truth is that worry, it's not a bad thing, but for me, it always needs to be in tension with the amount of wonder and delight that it also has a potential for doing. So when I think back to my own experience with computers growing up, it was full of a lot of that wonder and delight. It was, my family's first computer was the Commodore VIC-20, which the pitchman was William Shatner, who referred to it as the wonder computer of the 1980s. And my early programming experiences were with fractals and screensaver-like things, and there was
flying toasters.
Yeah, exactly. And SimCity and these things, there were all these wonderful things that I felt kind of connected the human to the machine as opposed to kind of distancing ourselves from it. And so I think the larger perspective of the book is also just is to also recognize that in addition to this wonder and delight, also recognizing that when we think about computing and computation, it doesn't need to just be this branch of engineering or this thing of computer science. It really is this almost humanistic liberal art that when you think about it properly, it should connect to language and philosophy and biology and art and how we think and the nature of reality and all these different kinds of things. And for me, those are the windows and the lenses that allow us to actually kind of re-enchant not even just computing, but in turn, many, many aspects of our own lives and hopefully can repair at least a little bit of that kind of broken relationship.
But, it seems like the fear of technology, the fear of computation, fear of AI, that doesn't seem to be kind of diametrically opposed to the wonder and enchantment. It seems to actually recognize the power. I think the antithesis to the wonder and enchantment is kind of like, I don't know, a banal thinking of it as a random tool.
Oh no,
right?
And this is actually I don't believe the story actually made it into the book, but so my grandfather, who I think I might mention in the book, he lived to the age of 99. He was a dentist and then eventually retired dentist as I got older. And he also read science fiction since the modern dawn of the genre. He read Dune when it was like serialized in a magazine. Like he knew all the stories. And I remember when the iPhone first came out. So I went with him and my father to the Apple store, and we're playing with the new iPhone, kind of checking it out. And at one point he goes, "This is it. Like, this is the object I've been reading for all of these years." And like, we've gone so rapidly. This is exactly what you're saying. We've gone rapidly from, wow, this is a moment of science fiction, to complaining about camera resolution or battery life, or I don't know, the app's not doing exactly what we want. And right. And I think that, and I think the fear is certainly a concern because it cuts off a certain amount of like playfulness and delight, which I think is very important. But I agree that even more than that, we have to make sure that we recognize the sheer wonderful nature of computation and kind of how it can connect to all these things. And if we view it as, right, just sort of this very, very normal, boring stuff, then we miss something out, or we miss out. And I think, right, and the goal of the goal of the book is to really rekindle that sense of wonder and almost like re-weirden. Almost like kind of like bring back like a weirding sense of what these things are, which is why I use some of this aspect of like the analogy of magic, which is like it's not just magic of like, oh, it's magical, it just kind of works, which sometimes that's fair with technology, but more so that it is computing is the culmination of the desires that we've told ourselves and wanted and mentioned in our stories and our fantasies for millennia, of like using words and text to coerce the world around us. And we should realize that is an amazing thing that like until, I don't know, 80 odd years, 75 odd years ago, with the advent of digital computers, we couldn't do this thing where we actually use text to control the world. And now we actually have code that can do this. And of course that power has changed, and there's lots of details and caveats and everything like that. And we don't want to push the analogy too far before it breaks. But recognizing that fundamental feature of reality, that we actually have this weird information stuff that can actually work in the real world, that's amazing. And we should pause at least and say, wow, that really is incredible.
Yeah. I mean, do you think that your appreciation of the magic of, say, AI is enhanced or diminished by your understanding of the nuts and bolts, right? Like how it's made? Because in some sense, right, if it's like, oh, I input this and it outputs that and it's a black box, like that's pretty amazing. But on the other hand, if you've actually built this thing and you know that it's, constructed on a set of, words and commands, like that's pretty awesome too.
Yeah, I would say, I could think about this by analogy with the way scientists talk about understanding the world and whether or not that lessens our appreciation for it. And yes, there is something to be said for just kind of looking at the world and its beauty. But the more you understand reality and physics and biology and chemistry, you gain this unbelievable appreciation for how these things work. And I think it's the same kind of thing with computing. On the one hand, yes, when you see sometimes how certain things are done, and I remember this years ago when I was an undergrad and learning a lot of kind of like the good old fashioned AI kind of thing, which was much more algorithmic and not as much kind of machine learning oriented. You learned these algorithms and you're like, oh, this feels kind of like a trick, but it works really well. And then sometimes that did lessen things, but certainly now when the systems we're building, especially these AI systems, are so complex, they rival biology, and at least in terms of how we're describing them, of like having an organic level of complexity, and we have to almost approach them the way biologists do, where they're trying to understand bits and pieces and slowly understand these things. I find that incredibly powerful. And especially there was, I think at one point early on, when ChatGPT was first released, there was this whole meme about like the Shoggoth, where it was kind of like this weird like Lovecraftian monster that we don't understand. But then with like the reinforcement learning with human feedback, we kind of put this like little like smiley face mask on top of it to make it much more understandable. And for me, the fact that I kind of learned a little bit about how that training worked and how it operated, and seeing all the weird edge cases of like, oh, here's some weird token or like this phrase that's a token that no one really understands why it's there. Like all these weird edge cases gave me a much greater appreciation for the sheer weirdness and alienness of some of these systems. And I'm not sure I would have gotten that if I didn't actually try to interrogate or understand these systems as I did, if I kind of just took them as given. So I think, yeah, sometimes so I would say there's the magic of just not knowing how things are. And I think that's kind of like people sometimes want to preserve that mystery for a certain amount of magic. For me, I actually think the wonder can be often enhanced, and sometimes enhanced greatly, by understanding something, whether it's the natural world or, in this case, our computational and technological world.
Yeah, and one of the fundamental things about code and computation is that you're converting word into action, right? And in a way, in the past, the only way you could convert word into action was, I guess, commanding other humans, right? So you could say, go do this, and, they would do it. But now it's more like, abracadabra, and the door opens, it's
correct.
It used to be the realm of fantasy, and now it's the realm of reality.
Right. And right. It was, and we have always used words to kind of coerce the world around us, in this case, getting other people to do things, which sometimes they do, writing books to maybe change people's minds. But you're right, only with the advent of computers can we say, okay, here is a very rigorous, structured way of doing something. Now do it. And of course, in the act of doing that, we end up recapitulating some of the stories we tell ourselves, which are like The Sorcerer's Apprentice, which is like, oh, here's the thing that I think it should do. And of course, here's all the unexpected consequences, like whether it's like, hey, Mickey with the broomsticks and the water and the buckets. And we begin to realize that there are all of these unexpected consequences. And for me, it's always like seeing the way, the richness of both the world and the computational world, and the way in which glitches interact and reveal the gap between how we think the system should operate and how it actually does operate. That in turn is actually really, really interesting, and of course leads us to further understanding of these kinds of things. But you're right, it's one of these things where the more we actually play with these systems, we sometimes actually end up doing some of the stories and like learning from those stories that we have told ourselves that are sometimes really exciting, sometimes cautionary tales, but we can learn from all of them.
Yeah, and you make a lot of comparisons between sort of the history of code and the literary history, right? In particular, the kind of Jewish tradition of literary interpretation, right? And I mean, this seems like an effort to bring computer science into the humanities, right? To make it an extension of the humanities. And, of course, we always talk about there's the STEM over here and there's humanities over there. And I guess, why do we think that way? Why do we have this dichotomous view, and why is it kind of mistaken in a way?
I mean, perhaps one of the easiest explanations might just be that as we've learned more, and we've had just kind of this increasing burden of knowledge, so to speak, we've had to specialize, and specialization is not a bad thing. I mean, like, experts really know a lot about a very small, narrow body of things. But as a result, we then discover, that we often kind of stay in our own little area. And I think computing is one of those areas that, even though it is very much kind of thought of as this like scientific or mathematical or engineering discipline, it has roots in lots of different areas. So especially like the early artificial intelligence, they were thinking about lots of different things. If you look at like the early years of computing, they were doing interesting things in biology. And of course, there's it touches upon lots of different ideas from philosophy. And of course, a lot what I include in the book is these kind of humanistic ideas and ideas from the humanities. And for me, that's kind of my attempt to say, no, like, we actually should try to smash these things together. One, because I think it's really interesting, but I also think that all these different domains have things to offer each other. And so, one of the ways I can think about this is, one of my, I guess, disciplinary roots is in the realm of complexity science and network science. And so network science is kind of based on this idea of like sometimes abstracting away the details and kind of connecting, like looking at large systems with lots of interacting parts and trying to understand these networks in the abstract. Of course, the details matter, but sometimes also looking at the abstract structure can be really powerful. And this is back when I was a postdoc. And I remember I was on some like network science mailing list, and I feel like every week there would be someone who would email and say, like, how do I measure this specific thing within a network? Or how do I do this thing? And of course, someone would invariably email back, oh, this has been known in sociology or physics, like for 30 years or whatever it was. And for me, that just kind of brought home the idea that we really need to cast this very broad net. Now, of course, with jargon barriers, it's really hard to overcome jumping from one discipline to another, potentially with certain developments in AI that will make it easier to actually kind of can like actually explore all these different areas. But for me, I definitely think that being deeply versed in the humanities can show you lots of different areas. Yeah, whether it's like understanding like the Jewish textual tradition or the way in which ancient mythological tales have evolved over time. These things are not so dissimilar from open source evolution or other kinds of areas. And if we only stay in our own little area, we're going to lose all the wisdom of these other areas and these other domains that have been thinking about these things for a very long time.
Yeah. Well, maybe you could talk a bit about the evolution of computational languages, programming languages, right? Because, it does look like evolution in a way, but of course, the evolution of stories, whether they're Homeric myths or whatever, they also have this kind of, evolutionary trajectory. And one question would be, why is it that we keep creating new programming languages, right? As opposed to having the existing programming languages kind of evolve. And why is it that we don't kind of, I don't know, see the creators of these programming languages as, I don't know, inventors? Like if I said to you, hey, who created Python? Like, I don't know anybody that could tell me. Even CS majors can't tell me like, oh yeah.
Who was it? Guido Rossum, I believe.
In the book you talk. Who created Fortran? Who created, Perl?
Bacchus, I think. But yeah, Perl is Larry Wall. He's actually a really interesting guy. I can tell you some stories about that. But yeah, I'm sure I'm the exception, but I agree. Right, like these people, they have, right, they're creating like an entire world, like because it's not just, oh, here's this like tool that you guys can use. It's this like meta tool where it's this thing of like, you are now going to think to a certain degree in this language and going to use this to actually develop whole new pieces of it. So it's a software to create other software. And actually,
by the way, I think you're the first person I've ever heard use the Sapir-Whorf hypothesis and apply it to programming languages.
Oh, really? I am certainly not the first. But well, I appreciate that. But the Sapir-Whorf hypothesis, right, is this idea that which it only really works in a very small way, kind of at the edges of language. But it's this idea that the language you speak will somehow affect or impact the actual kind of thoughts you can have. And so like the extreme version is kind of like from the movie like Arrival, where it's like, oh, like once you start thinking in this non-linear language of the aliens in the movie, then you're going to actually perceive reality in an entirely different way. That's not quite, we can actually translate from one language to another, and basically everything. We might not have a single word for those kinds of things, and the connotations and nuances are a little bit different, and you can see some perception differently. But I do think when it comes to programming languages, there is at least some, I don't know if literal truth to the Sapir-Whorf hypothesis, but at least some sort of like spiritual truth, where actually some people do feel that certain languages are easier for doing certain kinds of tasks. And you can see this with like the extreme languages. So there's a whole realm of what are called esolangs, which are these esoteric languages, which are designed to almost be like works of art, just kind of like, let's make some weird language that has some weird restriction. So an example would be this one is specifically designed to actually make it very hard to process language. So are we allowed to curse on this podcast?
Sure, yeah.
Okay, so the language is called brainfuck. And so it uses like this very small set of essentially punctuation. And it's this very weird, and it's entirely equivalent to every other programming language in the same way that every human natural language is essentially equivalent. But even though they're equivalent, it doesn't necessarily mean that everything is easy to do in brainfuck. In fact, everything is really, really hard to do. And I think that is sort of ultimately the desire that creates lots of programming languages, which is when someone builds a language or someone uses a language and realizes that there's something they can't quite do in that language, and they're like, oh, I want to make something else. And so for example, so I mentioned Larry Wall as the creator of Perl. Perl is this kind of crazy language, but the philosophy underlying it is fascinating, which is he actually had a certain amount of linguistics training. And so he wanted Perl to not necessarily tell you, oh, this is the kind of way you should be writing your language or your programs. He wanted to be as expressive and as open-ended as human natural language. Like in English, I can write a shopping list. I can write a haiku. I can write like a postmodern novel. I can do all of these different kinds of things. And he wanted a language that was as open-ended and non-judgmental. And I think he refers to it as like an amoral artistic medium. And so he kind of basically took all the best ideas that he could find from every other language and just threw them into there. And actually, you can, and I think he's still around, and you can find interviews with him where he's talking about some of the ideas that kind of underlie the invention and development of the language. That language also, he actually does build in a certain amount of kind of evolutionary ideas. I think the language, at least initially, did evolve for a little while. The problem, though, going back to natural evolution versus linguistic evolution versus programming languages, is in human language, if I say some phrase or use some jargon, and that you're not familiar with, your brain just won't stop. You might say, oh, I don't fully understand that, or you kind of skip over it. Or if you read a word or phrase or some ungrammatical thing to your own mind in a book, you won't break down. But computers are not nearly as flexible. And so,
right.
So as a result, there has to be almost a keeper of that language's description. And so it has to be fixed, at least to a certain degree. That can evolve. And so oftentimes, and so it can evolve from version to version, but oftentimes programming languages, they evolve in the sense of this language took the best ideas from the following 3 languages. And so it's so rather than just having one or two parents, you might have many, many parents. And so you can actually draw these graphs and charts and understanding kind of the evolutionary tree or graph or whatever, however you want to describe it, of programming languages. And it's wild. And it's amazing to see there's different families as well, in the same way that we have mammals and fish and birds and things like that. The same thing is true with languages or with programming languages.
Well, more Indo-European languages versus
right. We have natural languages that are kind of Indo-European and other kinds of languages, and we also or Anglo-Saxon languages or I guess Germanic languages. And the same thing is true with programming language. There will be ones that all are kind of iterative, or ones that are functional, or ones that are stack-based, or whatever it is. And of course, it's fuzzy around the edges, and you can use every single one to probably do something else. That's also one of the other weird things, which is this, and I kind of alluded to it earlier. It's this notion of Turing completeness, which is that once a language becomes of a certain level of complexity, then every other language is effectively equivalent to it. But going back to brainfuck, it doesn't necessarily mean that it's easy to write things. And so even though they're equivalent, which is kind of this interesting evening of computational power, there's still a lot of creativity available for people to do lots of different things there.
Yeah, I mean, I remember when I was doing my PhD in history, everyone had to know a second language. But if you were an Americanist, you could have a programming language as your second language. And I remember thinking, hey, wait a second, that's not the same. That's cheating, But
that's amazing, though.
Right? But it is. I mean, it is another language. But, maybe you could talk a bit about how over time, right? I mean, people had to write in binary, right? At some point, machine code. And over time, what's happened is that the languages have become ever more abstract, right? And they've begun to get closer and closer to natural language. And of course, now everybody's saying that the next programming language will be natural language. Now, I don't think we'll get to the point where we'll be able to, every nuance and sarcasm and all that stuff will work. You still have to be very precise, but still, what does that mean for us if the programming languages start to converge into natural language?
Yeah, so the way I kind of think about it is actually by an analogy with a story from the Jewish Talmud, which is, so it's the story where Moses is talking to God, and they're having a conversation, and God says, oh, there's going to be this unbelievably accomplished rabbi far off in the future. And Moses says, show him to me. And so there's also this weird proto-time travel moment where he gets whisked to the back of the house of study, and this rabbi's talking about things, and Moses, who has received the law himself, has no idea what's going on. And he's totally confused until the very end, where this rabbi says, oh, and how do we know this is true? Because of the law that Moses received from Sinai. And at that point, Moses is calmed. He realizes, even though he doesn't understand it, he realizes there is a direct line. There's this kind of tradition of the law. And I feel like the same kind of thing is true when we think about programming. Programming has changed. It has changed a lot. It's changed a lot even in my own lifetime. Where, I never programmed in binary, but like, yeah, people started in binary. They actually started initially with like wires and switches and things like that. It was very physical. Then it went to like
analog computing, right?
Well, that's even a whole other thing. Yeah, but
crabs. I was like fascinated by the crab computing.
Right. Yeah. Great. So there's all these ways you can abstract things. And again, we had like switches, and then we had binary and punch cards, and then eventually to like machine language and assembly language, which is kind of like a more human readable version of the machine, like binary code. And then eventually these higher level languages like Fortran, and then we had like C and C++ and Java, and then eventually Perl and Python, right? And now we're going to this next level of like vibe coding, or kind of using AI to create entire bits of software. And for me, yes, all these things are wildly different. On the other hand, though, like they are all part of this same tradition, which is trying to take ideas in our minds and instantiate them in machines and actually have our machines do our bidding. And so for me, from that perspective of recognizing, yes, all these things have changed, but they're all still part of this same tradition of trying to encapsulate ideas in computation, I think that makes me a little bit calmer. But in terms of what you're saying of like, if we can actually get to the point where it is kind of much more natural language, then I think there's actually a lot of really interesting possibilities. On the one hand, I do actually think that, natural language in many cases is actually quite messy and rough and ambiguous, and oftentimes computers do not do well with that. And when you ask, and you actually learn a lot about the task you actually are trying to solve through clarifying and working on the problem with programming. That being said, I think if you understand programming to a certain degree and can also understand very clearly the problem you want to solve, this vibe coding or AI generated code can unleash a huge amount of creativity. And so there's so the novelist Robin Sloan, he has this wonderful essay where he talks about an app as being a home cooked meal. And I love this idea because it's really saying that ultimately, like right now, if we need the traditional modes of software development and software creation where you have to work really hard and know this very specific detail, then the only kind of software that ends up being developed is the stuff that actually can get huge amounts of funding. Not entirely so, but often so. Versus if everyone can build the thing that they want just for themselves, that opens this huge amount of creative potential. And so in the same way that like an app can be a home cooked meal, like just because like every time I cook, I don't need to be cooking for like, I don't know, an entire stadium worth of people or an entire organization for like a conference. I can just cook for myself or my loved ones or whatever it is. And that can be really powerful. We should be able to do the same kind of thing with software. And in addition, what that means is that we can have much more personalized or single-use software. Whether or not the vibe-coded software is actually going to be useful at like industrial strength scales, oftentimes it's not nearly robust enough for that kind of thing, but it is robust enough for getting the things done that you need to do. And I think that kind of open-endedness and possibility is really, really exciting. And so, so I'm not quite sure what programming is going to look like in the future. I definitely think you can generate things using natural language. I actually think probably the most powerful programming experience is going to be some combination of natural language and very precise code. But yeah, it is really exciting to see what will be unleashed.
Yeah, it's like going back to the days of when, you're a kid. I think you in the book describe how your dad created some software for you to like learn stuff. And and so, we're now back in those days, anybody who had a computer could create code, and obviously it was a very small number of people. But now, like pretty much, I just taught this course last spring on agentic AI, and had my MBA students, many of whom had zero coding background, and they were creating these agents, right, using these no-code, low-code, drag-and-drop tools to automate like big chunks of their life. It was pretty cool.
Yeah, no, it's amazing, right? I was very fortunate that my father knew how to program, and so when we had the Commodore VIC-20, he made these like simple educational programs for me. Like it was kind of like a flashcard kind of thing, which I actually don't have a memory of, but like I think I found it years later in the basement. Some of like the things he had written about it, and I was talking to him about it. But that for a long time was very much the exception rather than the rule. Everyone though should be able to do this, and for me, like I had like early experiences with HyperCard, which is another one of these kinds of tools that helps democratize some of this kind of thing. But I think that this idea of being able to democratize software creation is incredibly powerful. And actually, in going back to the analogy with magic, yes, in many of the tales of magic, like it did require a great deal of effort. Like you had to apprentice, or you had to, I don't know, go to Hogwarts for 7 years or whatever it is. But there also were stories of like magic for everyone. There were spells that could be used by people if they, like in the Middle Ages, if they had, I don't know, lost their cattle and they needed to recover it. And I think we need that same kind of thing in the software realm as well, which is we need spells and code that can be used for everyone. And now with this ability, it's unbelievable to see.
Yeah, when I'm having trouble finding a parking spot, I say, "Hail Mary, full of grace, help me find a parking space." It works every time. I mean, I haven't yet had a problem. It seems to work, right? No, but I mean, you talk about it like Excel. I mean, in a way, all of us have been programming to some degree, right? So when you create an Excel spreadsheet and you input a formula into a cell, I mean, that's programming, right?
Yeah, right. Yeah, many of us don't think about it that way. We think of it as just, right, it's a spreadsheet thing, and it's kind of this like maligned part of the world of like, oh, spreadsheets, oh, they're terrible, whatever. And sometimes they can be terrible, but you're right. When there is this visual aspect of it, yeah, you can put formulas and you can manipulate the information that the formulas are operating on. That is programming of a certain degree. And it turns out you can actually do some really sophisticated things in spreadsheets if you want to. At a certain point, you probably should just use a more traditional programming language because then things will get kind of messy and weird. But I think like recognizing that a spreadsheet itself is programming of sorts should make people realize, right, they've chances are good. They've been doing this for a long time. They haven't realized it. And then maybe that will also kind of lower a certain amount of the concern or the fear of like, oh, programming and coding, like, no, this is not for me. And so, yeah, recognizing we've already been doing this, and now with AI, it's that much easier. I'm very excited to see what are all the use cases that people can use, because this is also the interesting thing is software developers are really good at building software, but they still need to often engage with the end users and the experts, and being able to actually, and so there's this idea that's been around in programming for decades of like end user programming, which is exactly what this democratization of code is, which is allowing the end user themselves to program the software for the needs that they themselves have. And I think that's the thing that really can open up a lot of possibilities, is when you yourself can build the thing as the end user for the specific use cases that you need, for the problems you have and the various solutions you want to solve, or various different things you want to solve. That will unleash things that many software developers, can't even hope to imagine.
Yeah. And the cool thing is, of course, if you do devise a solution to something, you can post it somewhere and someone else can use it, right? Put it up on GitHub or the equivalent. And you talk about how all of these very complex edifices, right, that are built out of code are really, in many ways, built out of components, right? Like routines, subroutines, Lego bricks, drag and drop. And, so it's all, I like to say that when I talk about a corporate software stack, it's like a chimera. I mean, you've got all these different like pieces of chunks of DNA that are kind of stapled together, and only a relatively small part of it is homegrown. Most of it is off the shelf, right?
Yeah, and this is fundamentally this idea of like abstraction, which is this idea that within computing, but also just more broadly, like that if you abstract away the details, you kind of don't need to know how these things work, and you can just kind of use the higher level components. And so whether it's like some more complex data structure, or with open source software, other packages that you can combine and put together, what that means is that, right, you're never really starting from scratch. If you understand all the components that are pre-existing that are out there, then you can recombine them in novel and exciting new ways to build all these things. Which, I mean, the downside is that when you have all these pieces together, that there might be a like reduced understanding of all the different things and how they interact. And of course, then you'll have situations where like there's one little thing that everyone relies on, and it turns out it's actually only being maintained by like one part-time person who's like under-resourced and overstrapped, or like really doesn't have the time to do things. And then of course there's some weird bug. But for me, like overall though, the ability to combine all these different things together really does, right, it unleashes this kind of open-ended sort of complexity where you have all these components, kind of going back to like the Lego analogy of like, then you can kind of put things together in new ways. You have all these bricks at your disposal and build new things. You don't have to start, and when you're building Legos, you don't have to spend all the effort to, I don't know, figure out like the actual shape of the pieces and build a factory to manufacture. No, you just kind of take them as given and then build the thing that you want. And the nice thing is that, at least within software, when other people build those things and then release them or make them available to other people, especially sort of through the entire open source ecosystem, is that then now that is a new brick, and then you can kind of use that. And so and one of the things I was talking about with in terms of like coding, like I mentioned this I think early on in the book, like when you think about code as like, oh, it's just like following a recipe or whatever it is, but it's also much weirder because each of the little pieces that you're including in the recipe, they could themselves be these huge, giant things that you really can't even unpack, or you don't really even want to unpack. And that this kind of, I don't know, like this kind of ladder of recombination is one of these unbelievable things that is available, particularly within code, because it is to a certain degree, like it's just information stuff. And so there's very little effort required to just kind of copy it and then make it your own and then play with it. Now, of course, there's a lot of work of maintenance. And I think that's one of the things in the open source world that a lot of people don't necessarily spend as much effort on, or not necessarily effort, but it's not focused on as much. And so as a result, people don't pay it as much attention as they should. And maintenance is actually one of the really important aspects of open source. But by and large, overall, just this idea of like open-endedness and recombination and using all these bricks, like these pieces, it really can do unbelievable things.
Well, you were trained as a biologist, and so you are highlighting in the book a lot of the deep similarities between biology and computation, right? And, I like to say that we are fundamentally built on software, right? I mean, our DNA is effectively code. And we also kind of have a Lego brick construction where there are specific sets, bits of code that create proteins and so forth that come from our ancient ancestors. And, we're just getting more and more complex over time. You called for kind of a unified field theory of information. I kind of like this, right? Where biology and computation should be seen as, just subunits within this broader field of information studies.
Yeah, I mean, I'm certainly not the only one to kind of think about these kinds of things, but I think, when we think about computation, we think about it as kind of this like very like traditional sort of like programming kind of thing, or the kind of computation that happens on your computer. And then you have biology, and there's kind of two modes of thinking about it that I kind of highlight in the book. One is the kind of informational mode that you kind of talked about, where there's this like DNA becomes RNA becomes protein, and these are modular, and there's a very kind of bioinformatic way of looking at it, which I think is really, really powerful. And then you also have kind of the mess, which is just the fact that within a cell, you have things that are kind of vibrating at high degrees, and really everything is actually quite statistical as opposed to regular. And then at the higher level, we're kind of these weird squelching messes that leak and creak. And the truth is that biology is both of these. But in addition to that, biology is also information processing, but it's a very different kind of information processing than the traditional kind of computational realm that we have. So in the book, I also discuss, so there's this idea of artificial life, which is kind of abstracting away details of life to kind of encapsulate it within computers. And one of the ways people describe this is life as it could be. And I feel like what you're talking about is almost like computation as it could be. There's the biological approach to information processing. There's our traditional computational approach. And those are really kind of smaller things within this larger superset of how to think about how we process information and compute. And there should be so many different ways of doing that, whether it's analog computing, parallel computing, biological kind of computing, these other kinds of like unconventional computing that people are beginning to think of, like when you use slime molds to do optimization theories or whatever it is. And I think we just need to really broaden our view of like how we think about computation, because yes, it is. Computation and code and kind of the traditional modes, they are really, really powerful. Biology is also very powerful. We can learn a lot from how biology does its stuff, but also recognizing that, right, these things could just be a few points in some massively high dimensional space that is really also very valuable to explore.
Yeah, I mean, you talk about every kind of way of understanding the world is lying on this continuum from Laplace to Lovecraft, right? I found that interesting, right? I mean, because it does seem to describe how whatever discipline you're in, trying to understand the world, like there are these kind of regular patterns and rules, and then there's this like messy stuff, right?
Yeah, so,
You know?
yeah, this is a little bit different than the biology, but yeah, I think that was probably in context of like simulation. But right, yeah, this idea where you have like Laplace, like this, like the French physicist who kind of said, okay, you just know the position and like the position of all the different particles in the universe and understanding the way in which they interact, and you can really just run everything. And having this kind of,
and this would be like closed form solutions, right?
yeah,
Where,
that,
you know,
or even just like saying like if we just had enough data and a really well understood simulation model, then we could actually just like have this kind of reductionist sort of simulation of all of reality. And then H.P. Lovecraft is, of course, the horror story, the horror writer who was like, yeah, you might think you understand the world, but really we're just kind of like sitting on this like dark sea and like kind of paddling like ignorantly, and like who knows what's going on underneath. And the moment we understand the true nature of reality, we'll kind of go mad. And there are all these like horrifying ancient monsters, and it's like much more complicated than we can ever imagine. And of course, I mean, setting aside the whole like tendency towards madness that he always talked about, I do think that in truth we lie somewhere in between. I think we want to really think that we understand the world in its entirety when we simulate things. And certainly when we are trying to predict the world or predict weather, we kind of tend towards that kind of Laplace approach. But at the same time, though, we have to recognize that there are limits. Like our data is limited. The ability to predict outward beyond a certain amount of time is limited. We are not in a state of total and utter ignorance the way that Lovecraft might think. But we do have to recognize our limits. And I think that kind of that sense of humility, I think, can actually be, rather than it being like overwhelming, actually can be very powerful to kind of say that, yes, there might be limits to what we understand. We should still try to continue to understand the world. But these models and these predictions are going to have limitations. Now, of course, especially when we build computational models, prediction is really only one reason we do that. And I think if we're kind of viewing it from the perspective of prediction, if we tend towards the Lovecraftian model, it's going to be disheartening. But if we realize, oh no, wait a second, there are lots of other reasons to have models, such as, I don't know, gaining an intuitive understanding of something or simplifying something to gain some mental hook, then it doesn't necessarily mean that we have to capture the world in all of its complexity in our models. In fact, sometimes that's a bad thing because that means we can't understand it. And so we have to also, so simplifying things can also be a very powerful tool to understanding this. And I think, and for me, that's one of the powerful ways of like balancing between the Laplace and Lovecraft kind of tendencies.
Yeah, and it seems like some of these techniques like simulation, I mean, they allow us to see things that we couldn't otherwise see, right? Because they're just too complex. I mean, partially it's about helping us to get there more quickly. I mean, you talk going all the way back to Vannevar Bush about how, you know, if you can kind of map out knowledge in some way, then you can get answers more quickly. I love this example that you pointed to in the book about how if you just applied an LLM to, right, the knowledge graph around different materials, you could surface some discoveries which took forever, but which could have been much more quickly achieved, right?
Yeah, right. This is this idea that right, if you can pour all of human knowledge or human scientific research into one of these language models, and I think actually this one wasn't even like the most sophisticated. It was a fairly simple one. It might have even just been like one of these like embedding models, but recognizing that a lot of these models operate on this idea that you are placing knowledge and information and papers and words and text into this kind of latent space, which is this high dimensional representation of all these kinds of things. And that allows you, right, to navigate that information. But also you can see the spots where things might be connected in ways you hadn't expected, or the gaps there. And yeah, in that specific paper that you mentioned, right, it was looking at material science advances, and it showed that if you had actually placed all of that information with it, I think certain, I forget exactly, the deal might have been like around like piezoelectric, I'm not even sure I'm pronouncing that correctly, but some specific kind of material science property that some people would have known that this specific material actually had that property several years before it was actually discovered, because the way in which people talked about that property was also very close to the way in which people talked about that material, which is, I mean, the truth is that is also, I mean, that is kind of the most recent iteration of some of these kinds of things. So I actually, in my first book, The Half-Life of Facts, I talk about this paper by an information scientist, Don Swanson, about undiscovered public knowledge. This idea that because the scientific literature is so large, like it should be easy to imagine that there is a paper that says somewhere A implies B, and there's another paper that says B implies C. But because no one has actually read both papers, even though it might very well be true that A implies C, by combining them, no one knows this. And so he was not content kind of leaving this as a thought experiment. And this was like the mid 1980s. He used cutting edge computational technologies, which was like searching keywords in medical databases. But he actually found a relation. He ended up finding a relationship between like consuming fish oil to help treat some sort of circulatory condition, and then I think he eventually published it in a medical journal, even though he was just an information scientist. And of course, since then, we've had more and more sophisticated ways of using these computational tools to navigate knowledge itself. And so I think, and now more recently, people are talking a lot about these like AI scientists and computational science, kind of computationally generated hypotheses and experiments, or even scientific research. And I think there are certainly still hurdles there, but I definitely think there's some really interesting ways of not necessarily eliminating the need for scientists, but allowing almost for this like human machine partnership, at least when it comes to discoveries, for generating new hypotheses and new ideas, allowing scientists to navigate the landscape of the literature much more effectively. The ability to do some sort of literature review, I imagine, must be completely overhauled by now. Obviously, there's something to be learned from actually kind of like going through paper by paper. And I was talking about this with someone recently. But at the same time, though, the AI is able to do a lot of these things very, very rapidly. And so there's always going to be some trade-offs. And I think these kinds of things are really going to change how we do literature search or navigating science or even doing new science.
Yeah, I remember when I was in grad school, I'd go to the stacks and I'd wander around the stacks. I mean, I don't know if you're old enough to remember that.
Yeah.
And just pulling stuff out kind of at random, and like nobody does that anymore. We have that kind of done for us.
Although that being said, I'm reading currently a new biography of the Nobel laureate physicist Luis Alvarez, and I think in it he mentions, I think he was told by someone, like the way to kind of very quickly navigate that kind of thing is you look to see like the discolored parts of the literature of like these journals of the journals, because that's the stuff that people are thumbing through, and so it has like their finger oils or whatever it is, and so you can see those kinds of things. And so like there are ways of like navigating that stuff as well. And sometimes, having that kind of human touch to use those things as a way of navigating and finding what are the most important bits of knowledge, that can be very useful. And of course, we have proxies like citation counts and things like that. But especially when things are new, those are not, you need still a little bit of the human sometimes there as well.
But, I think it was the CEO of Moderna who said, I run a software company that makes drugs, right? Which I think sort of highlights this idea that these tools are being used to, not only create solutions, but to generate hypotheses.
Yeah, no, right. We are using, whether it's like truly software is eating the world, or just kind of this idea of like that we need computational approaches to navigate knowledge, right? Like that is a very, very, it is a very important thing. And I think it goes back to almost the liberal art kind of approach, which is not only is understanding computation important for understanding lots of other things, but it is becoming more and more deeply embedded in every aspect of what we do, including pharmaceutical discovery.
Well, I want to get back to this point you made about, we're talking about natural language. In my classes, I have a lot of my students who are quoting folks like Mark Benioff, who say, in the future, for every human employee, you'll have 1,000 agents working for you. And, obviously, I'm not so sure that this makes sense, right, to think about these agents in the same way. But there is some logic to this. And the idea is that if you're good at managing people, there's a strong overlap between that and managing these, agents, right? I mean, you have to know how to delegate. You have to know how to provide instruction. You know how to provide feedback. You have to know how to, exercise oversight. I mean, it seems like there is now a general skill of management, which you can apply whether you are commanding some kind of carbon-based life form or some kind of silicon-based system, right? I mean, aren't there deep And I know they're different, and I got into big trouble when I was giving a talk, and I said that, ChatGPT is kind of like an autistic employee in a way, right? Because if you're on the spectrum, you kind of take things literally, right? But I mean, if you can manage that type of employee, you should be able to manage this type of system, right?
Yeah, and so actually, one of my friends, I definitely think there is something to be said, yeah, for this kind of management approach. And like people have been talking about this idea that, right, you're going to be almost like at a managerial level, whether it's creating software or other kinds of things. A friend of mine, he also talked about it as almost this, that like everyone's job is almost going to be like playing a video game. Like in the sense of like, I mean, the way he kind of described it is like he has multiple windows open. These are all different agents and all different tools doing things simultaneously, and he has to respond to this one and this one, and it's kind of like it's a certain type of video game. But there is this like that kind of like managerial kind of approach. I would say the way to think about this though, right, is like to figure out, okay, what is the right level of like like management that needs to be done. So there's this book that came out somewhat recently called The Unaccountability Machine, where it discusses this idea around management cybernetics. And so there's like cybernetics from like the 40s and 50s and 60s of kind of like control and feedback and communication. And
Dan Davies, right?
Yes, exactly, right. And so this book is saying like, right, there was also this whole very kind of like UK based tradition of like Stafford Beer around using ideas around cybernetics to think about management. And so he developed this, like, it's called like the viable system model, where there's kind of like, there's 5 different systems and they have to interact in certain different ways. And he shows that if a system, like an overall system is really, if it doesn't have every single one and you're not managing like each part the right way that it needs to, those things break down. And so for me, I think one of the kinds of things we're going to have to train is not only because and these are computational systems, so they should be very amenable to kind of cybernetic kind of thinking. And so we're probably going to need to almost take some of those kind of management cybernetics ideas maybe a little bit more seriously and say, okay, when we're managing our many, many agents, are we managing them at all levels simultaneously? Are we managing them at the very low levels? Are we making sure that we're thinking about the overall philosophy and kind of being future thinking as well as coordinating and other aspects? Because if we don't do that very well, we are going to be very quickly overwhelmed by like when a game gets faster and faster and you're doing many, many different things, like that's not what you want to be doing long term. And especially if you end up managing these agents as basically your entire time, but you don't necessarily build in that kind of higher level management of taking the time to figure out, okay, like what are the right directions I want to be going in? I think we're going to, and we could be successful, but I imagine the downside is if you're not doing the management correctly, you'll end up privileging the short term rather than the long term, and that will also have some problems as well.
Right. Of course, those are the same problems that you have with ordinary organizations that have no, right? I mean, it's the same problem.
But it's one of these things where like now, I think if everyone's now playing with this, like we need to say, okay, you need to learn this stuff sooner rather than later.
Mm-hmm. Mm-hmm. Well, I mean, one of the problems I think with a lot of these agents is that they don't kind of ask for help in the way we'd like them to. And of course, obviously there's some humans do this as well, but what we want is our, say, ChatGPT to say, I'm not really sure about that. I could tell you something, but it's probably going to be bullshit. So maybe let me ask you a few questions before I go further. And of course, I think that that's not the natural next step. I think we're going to head there. But I think that the biggest danger right now is that people don't realize that these agents are not kind of asking for direction when they need it.
Yeah, and this is like the whole problem with like sycophancy within a lot of these systems where like when an AI tells me that every idea I ever have is amazing, I know something is deeply wrong because I know not every idea I have is that good.
Not every human knows that. When they hear that from other humans, they're like, I am really a genius, right?
And so, you need it to be able to say, I don't understand these kinds of things, or to push back. And there was something somewhere I was reading about like trying to get one AI tool to basically be more of like a kind of like a cranky professor, where it was like critical,
gadfly.
Like critical, but also like helpful and kind of like helping hone your idea into the best possible thing. That other, as well as these agents, they should be able to let you know when something's not going right or not understand right, because otherwise, if you're not being aware of these exceptions, it's going to be really problematic. And so I imagine some of these things will be ironed out, but these are issues.
Well, before I let you go, I want to talk about this book, Half-Life of Facts, because I really enjoyed this. And it seems like, I mean, this is something that everybody should understand. And I think to be a true scientist is to understand the contingency of everything that you believe, right? And be ready at all times to replace your beliefs with new beliefs. And I think you use this term mesofact, which I thought was never heard this before. And, there's this whole discipline of scientometrics, right? And so obviously, if you're a scientist, you understand that you're going to wind up replacing your beliefs. But what I think most people don't think about is that there might be some, I don't know, laws or rules or general principles that will allow us to anticipate the refutation of our beliefs.
Yeah,
there's some logic to this.
Yeah, and so the idea behind the book is that, right, like in the same way, it's kind of by analogy with half-life and radioactive materials, that like on the one hand, if I gave you a single atom of uranium or some radioactive material, I can't really tell you when it's going to decay. It might decay in the next fraction of a second, might decay in, I don't know, millions of years, whatever it is. But things change when I give you a whole chunk of uranium. Then suddenly it becomes very regular, and you can actually chart out this nice curve of decay. You can actually measure its half-life, how long it takes for half of it to decay. And the same kind of thing is true with what we know, which even though it might be hard for me to say, oh, this fact is going to be overturned or this other thing is going to become obsolete, there are these regularities to how what we know changes over time, whether it's looking at obsolescence within medicine, whether it's looking at the way in which scientific papers change over time, or just the way in which the facts that we know that are in our textbooks change over time. And so for me, right, it was trying to chart out some of these kinds of regularities, as well as also kind of the mindsets we need to adapt to constantly changing knowledge. Right. And so like one category were these mesofacts, which and it is not surprising that you had never heard this term before, because I made it up for the book. Or I made it up actually for an essay beforehand. And then, so it was a made up word. But right, it's the idea behind it is there are facts and bits of information about the world that on the one hand change very rapidly, of like what the weather's gonna be like tomorrow or what the stock market closed at yesterday. And we know that if I told you, oh yeah, the stock market closed at whatever, but like that was a decade ago, oh, it should be the same. Like, that's very out of date. You would not take that as like the way it is now. And on the other hand, we have facts that you can really learn effectively once, and you never have to worry about them changing, which are, I don't know, like the number of continents, or the number of fingers on a human hand. You learn them once and you're good to go. But in between, there are these facts that change on this mesoscale, the mesofacts that change on the order of decades or on the order of a human lifetime. And unfortunately, we learn those the same way we learn facts that also don't change, like effectively ever, or change much more slowly. And so for me, it was trying to highlight that there is this huge body of knowledge of things that we know, that we think we know, that are certain, but are actually changing slowly and steadily. And so for me, part of that is kind of using, well, sometimes like being willing to update your knowledge when you think dinosaurs look like reptilian monsters, and then your kid comes home and says, guess what? They're kind of like these very colorful chicken-like things. And you're like, oh, maybe we've actually learned quite a bit. And so that's actually really good to know. But also more broadly, we, in the same way you mentioned that scientists are really good at understanding this, I actually think that each of us need to have a certain amount of that scientific mindset. Because science, when properly understood, it's not just a body of knowledge. It's really a rigorous means of querying the world. And as a result, those queries are going to end up changing things that we know. And so, a professor of mine, when I was in graduate school, he told me this story. This is already after I had left grad school. And he was telling me this story that he once he was teaching some course, came in on Tuesday and gave some lecture on some topic. And then the next day, he actually read a paper that invalidated the lecture he had given the day before. So he went in on Thursday and he said, remember what I taught you on Tuesday? It's wrong. And if that bothers you, you need to get out of science. And I think that kind of idea that science, or what we know, is constantly in draft form, is a very powerful idea. It can be sometimes frightening for people. But the truth is, like, by and large, not that much is changing that rapidly. It's often like the things where, like, at the frontiers of knowledge, where we kind of know the least, but we're actually where the most exciting things are happening. That's actually where things are often changing. But we do need to be open to recognizing, that things can change. I mean, my grandfather, who I mentioned, he was a dentist, he learned the wrong number of human chromosomes when he was in dental school. There was like this weird period of like several decades where they were able to see chromosomes, but apparently not count them properly because they didn't have like the right imaging technique. And so he learned 48 human chromosomes instead of 46. And then we had a better way of imaging the nucleus, and then we updated this kind of thing. And so for me, I think as long as you kind of take that idea of recognizing that things are in this draft state, don't be like unduly skeptical and say, oh, therefore, like we don't know anything. Like we are constantly approaching a complete, hopefully a more complete understanding of the world. And actually, and like Isaac Asimov has talked about this of like where I think the science fiction writer Isaac Asimov, he got some essay, he received a letter where he was asked like, oh, we used to think the Earth was perfectly flat, then we thought it was like perfectly spherical, now we know it's actually not quite. How do we know anything? And he's like, if you think thinking the Earth is flat is just as wrong as thinking the Earth is a perfect sphere, it's like, then your view is wronger than both of them put together. And like you have to recognize like we are actually like asymptotically approaching things. Things will change along the way, but we have to be open to updating our knowledge. And I think certain fields where lives are on the line are more willing to understand this, of like medicine with continuing medical education. Sometimes they're even taught in medical school that like a decent fraction of what you learn is going to be obsolete within a few years of your graduation. But the truth is, nowadays, like we're all in that state. We should be more aware of that. And so, so the book was kind of my attempt to show the regularities as well as the mindset we need for adapting to constantly changing knowledge.
Yeah, but I mean, look, there are facts that change, and we know they change, right? Number of people on Earth.
Yeah.
You know, I remember I memorized all the capitals of all the countries back in 1972, and you know, I know that a lot of them are probably wrong. You know, I know that, but the other type of stuff is when the truth doesn't change, but our understanding of it does. Like, you know, what's good for you and what you should eat and so forth. And so, I guess the question is, in terms of pace. It seems like the pace of scientific knowledge and the pace with which we are, you know, learning new things. It used to be, okay, we moved from geocentric to heliocentric. That was a big deal. That kind of stuff happens every, you know, millennia or so. But, you know, Euclidean physics and, you know, relativity. But it seems like the pace is changing more quickly in terms of scientific discovery. But our capacity to manage that pace has not kept up. I mean, do we need to, I mean, I tell my students, like, everything you're learning in class, by the time you graduate, will probably be obsolete. So, you know, you should probably learn just how to learn as opposed to just learning. I mean, is that becoming increasingly important? I mean, is there a way to measure the pace with which the half-life of facts is changing over time?
And I'm sure there are ways, and it really kind of depends. Like there's lots of different ways of like thinking about what we know and how we learn it. And I think in some ways, some of these things are slowing down. Of like there was maybe a burst of like low-hanging fruit discoveries within certain things in physics, then kind of slowed down. Then maybe had another burst of quantum mechanics or so. So I'm not sure if it's always speeding up. It definitely feels that way for certain kinds of things. Certainly like technological change and even scientific knowledge, these kinds of, and certainly if you look at just like the number of scientific papers being released, like that has certainly increased quite a bit. And so I definitely think that having certain frameworks for learning how to learn, how to take new knowledge and assimilate it in a useful fashion as opposed to being overwhelmed by it, I think is really useful. I would say the one hopeful note is humans are actually really good at adapting. I mean, going back to when I was saying of like when we first got the iPhone, this thing was unbelievable, and now we just complain about it. And
right.
And so like that, and like ironically gives me hope. Like it shows that like we are really good at adapting to things. And so I think on the one hand, yes, it can be overwhelming. And I think some people, when they are confronted with all this of like, oh, I thought this food was good or healthy for me, and now they say it's bad for you, or now this other thing changed. Therefore, like we don't know anything. And of course, that's not the answer. I think just kind of throwing up our hands in despair and just giving up on learning new things, that is not a productive response. But I do think that if you constantly try to learn and like learn how to learn, we are actually really good at, as humans, at adapting to lots of change. And so so that does give me a little bit of hope of like, yes, it's overwhelming and there's a lot of change. But we often give ourselves far less credit than we realize for being able to assimilate all that information.
But we have to be kind of in perpetual adolescent mode or undergraduate mode.
Oh, correct. Right.
You know?
Yeah. We can't just say like, oh, because we have the tendency to specialize. When we were young, we learned a lot about lots of different things, and then we kind of like start learning like more and more about less and less until we know like a lot about some very small thing, until we're confronted by things changing. We need to just keep on learning about everything and like really, and I think maybe that's not even just learning how to learn, but like cultivating a certain mindset of curiosity. And I think maybe that's the key of like just really being curious about all the new things that are happening and different things about the world. And it doesn't need to necessarily be in a systematic way. You can go down rabbit holes and pursue your interests, but cultivating that curiosity, I think, is a really important and underdeveloped skill.
Well, I'm hoping I can develop an agent that will tell me what books to read, because right now I'm like just kind of all over the place. I need a learning map that is a little more systematic. But maybe if I had that, I might not have encountered these books, which sort of stumbled upon in the old analog fashion. And
well,
they're both
that is
fantastic.
A good problem then.
Yeah. So The Magic of Code, check it out. And also Half-Life of Facts and Overcomplicated. Thanks, Sam.
Thank you very much. This was wonderful.
Unsiloed podcast is produced by University FM, elevating the stories of your institution.